All right. I guess we're getting to the end. So my name is Tom Herbert, and I'm going to talk about a new protocol proposal that we're making. It's called Firewall and Service Tickets. So we have a problem. I guess everything starts with a problem. But in this case, the problem we have today is end host, applications, the host, even the kernel, basically our side of the equation doesn't really work together with the network itself. And what I mean is we both kind of live in our own little worlds. We're optimizing various pieces. The network does its thing. But for the most part, we kind of assume that the network delivers packets and we make them on our side, and everything works out well. So this model leaves a lot on the table, so to speak. So one way I would describe it is the user, are they getting the maximum benefit from the internet in the sense that can we provide the QoS, the differentiated services, the security, can we provide what they need just on the basis of these two worlds kind of acting independently? So my argument is host and network don't work together enough, I mean, for the benefit of the user. And again, the reason the need for this is we want to provide the best services for the user, which more and more we have to think in a holistic point of view from the application to the application. How do we get the best service, best value for the user? So the solution to this is we need host and network to actually talk in a meaningful way. And there's actually two parts to this. One I call host and network signaling. This is where the host has some information and it wants to tell the network, give the network this information. And this information is sort of like, for this particular packet, I would like this sort of QoS applied to it. And probably a higher degree of granularity than get with DivServe or some of the existing solutions, and certainly more granularity than we can get just by inspecting the current packet contents. So the idea basically is we're going to attach information to packets that is intended for the network to read. So host attach what we call a ticket, which is going to be a set of data, attaches it to to its packet. The ticket describes the services that the application is requesting from the network. And when we send these packets with the ticket attached, the idea is the network will interpret that. So it's not end-to-end. It's actually nodes within the network interpret the ticket, this information, and then the network applies the services expressed in that ticket. So it's very explicit in this model. And the value of this is we can provide very fine-grained, much better services than we can do. So that benefits the user. It obviously benefits the network providers because now all of this fancy hardware they're building and solutions they can use, give users better service, potentially monetize at various layers. And of course, host developers benefit because now we can provide more interesting applications. We're working with a network, we can scale and things like interactive video, real-time applications on the internet, they start to become more reality. So I would call this a triple win. Everybody wins. There's a fair amount of traction for this that I'll talk about in a little bit. So FAST is actually pretty simple. The way to think about it is we have an end-to-end communication. So we have an application on one side, application on another. Between them is a network or maybe multiple networks. So the first step of this process is the application needs to know what ticket to send. And one important thing about tickets is these are intended to be consumed by the network. So really it's the local network that consumes them, but it's also the local network that provides them. So it's kind of like a very strong analogy here is with tickets in real life. If we're going to, say, the Taylor Swift concert, seems apropos these days. So you go, you buy your ticket, and you get the ticket. And when you go to the door at the concert venue, you present the ticket. And that ticket allows access into the venue. And not only that, it has additional services like where to sit, and maybe it's a ticket package with concessions or something like that. So it's pretty much the same thing. So in this case, application wants to get services for some flow, and it sends this ticket request, and the agent sends back a ticket, which is kind of a blob that describes those requests. Now, the ticket isn't even necessarily readable by the application or the host. It can be encrypted, but the point is, when the application sends, it attaches this tickets to its packets. All it knows is this ticket represents the services I want. It can't decode it. It really has little information about what it means, but the meaning of it is interpreted by usually like the first hop router. So to read the ticket information, apply it, and then once it does that, it applies the services throughout the network. And usually what we would anticipate is only the first hop router has to interpret the tickets, because then it can put the packet into more network specific services like slices in 5G or diff serve, various priority queues, what have you. So it actually can map the ticket into more network specific mechanisms. So this is the forward path. We also have to consider, how do we get service on the return path? So it's a little more interesting because forward path is pretty obvious. I attach a ticket, I send it. The ticket lives at least to the point that the network interprets it, and then can continue on. So the idea of getting reverse service, so the application is doing a video download, saying we're doing a video download. When you do the request for it, that's really not interesting in terms of service. The service has to be high bandwidth in the reverse direction. So we may request that ticket is reflected, and then on reflection, the ticket is interpreted again by a router when it enters the network. And now we interpret that ticket and we apply services again through the network in the reverse path. So we can illustrate this with a little animation. So host gets the ticket from the ticket agent. It attaches the tickets to packet. The tickets are interpreted in the local network. And one thing I should mention is tickets really are very scoped. Usually they will only have meaning in the local network. So this is not something that is global wide. If you use a ticket in one network and you go to a completely different one, the ticket should not have any meaning in that network for various reasons. The security aspects also, we don't want to enforce some standardization of what tickets are across the internet, because then we get into that whole part of it, the standards process. So we kind of make this flexible. So it's only really interesting in the local network, but that works out because usually it's a local network where the services tend to be applied. Because when packets leave the local network and say go on the internet, usually we don't expect the internet to provide service differentiation. It's not really designed for that. But when we get to, say, an external provider, we're once again entering what we call limited domain, where tickets may be appropriate. So in this case, though, once the ticket leaves the local provider, it would traverse the internet and say go to the host. The host gets it. It doesn't know what this thing is, but it does know I'm supposed to reflect this in packets I send back. So all it does is takes this information from the receive side and puts it into the send side. This is actually a pretty common thing in protocols. So if you look at IOM, for instance, it will reflect the information back so that the sender gets the information end to end. So it's pretty common to do this sort of reflection. So the reflected ticket then traverses the internet back towards the sender. And once it enters the local provider network where the ticket was originated, then we provide services. And again, now we can get services through the last part of the provider network. And then we do have the option to verify the ticket. So you can imagine that this is kind of reflective of a dumbbell technology. If the source and the destination were in the same provider, then we don't have any parts where we don't traverse the internet. So that works easily. If you have a scenario where you have two providers like this, conceptually, both sides could actually request tickets from their local network. And so you could end up having multiple tickets attached, one for the provider on the left, one for the provider on the right. And the ticket that's applied is the one that's local to the provider. So the ticket that was provided in provider left would be interpreted by provider left, and the one provided for provider right would be interpreted there. So it's kind of a symmetric thing, and reflection works the same way. So real quickly, this is kind of more of a use case. So 5G, I think, would be a really good opportunity for a protocol like this. So in this case, we have an application that's trying to do video, probably 30 frames per second, 1080 pixel, 50 milliseconds, probably let's say it's an interactive video. So he wants to do a voice chat. That's definitely one where he wants services. It's going to be low latency, not necessarily the highest throughput. So we application requests a ticket. This would be like the chat server or chat client. Requests a ticket, gets the reply, and then we do that process. So first we send the packet with the tickets attached. That actually goes to something kind of in the 5G realm, a service mapper. It inspects packets and then maps that to service function chaining, or like I said, NFV, network slices, whatever the mechanisms are within the network. This is actually already exists today, but what they're doing today is trying to map source, destination, address, and port, which, like I said, is a lot less granularity and also requires, we're limited by the applications. Obviously something like Quick, where we're trying to hide that any information about the application, doesn't really work so well in that case. But like I said, so while we're in the local provider, so step 3, the packet's forwarded through the core, services are applied, and it goes out. In this case, it goes to the internet. So again, on the internet, the ticket is not looked at, not processed, but in this case, the application server does reflect it. And when it comes into the network, a little more validation is required. So we have to validate the ticket. So again, when you go into the concert venue, they have to validate that that ticket was actually printed by the network and issued. We can also have an expiration time to limit the time window. And there's some provisions here, or somebody has an old ticket because they haven't had traffic in a while, we might allow that through. So there are some provisions to allow tickets to come back in the network in a little more flexible way. But once it enters the network, the same sort of mechanisms apply. So we interpret that reflected ticket and put that into the provider network using those mechanisms. And then it eventually goes back to the host, and the host can take a look to see if it's valid. That last part isn't completely necessary, but it's probably better, good for logging, just to make sure that somebody's not spoofing tickets. So tickets are a type of what we call hosted network signaling. They will have some kind of necessary properties, especially in the internet. We think they have to be encrypted in some fashion and authenticated. So just like a real ticket, we don't want people forging tickets, getting services they didn't pay for. So in this case, we do need, kind of like a real ticket, we need security mechanisms to prevent abuse. Also, it's very clear we don't want somebody to get services that they aren't supposed to get. The expiration time limits the use. We can also have a revoked list. So if somebody is using a forged ticket, you could potentially revoke that, but that list would have to be propagated probably to all your edge devices, I suppose. And then reflection, there's a couple of properties of that: reflect, don't reflect. One thing that is kind of implied here, we really want a concise ticket format. So if we're attaching this data to every single packet, the overhead has to be kind of constrained. There's a little bit of a tension here because when you encrypt something, you kind of want to have more bits, but we need fewer bits for the overhead. So kind of some of the problems we want to work out is how to actually encrypt data like that. So it's a little bit unique of an encryption problem. You can also think of this, the number of nodes that potentially decrypt these things is much greater. It's not a one-to-one, one encryptor, one decryptor. So it's a 1 to n. So there is some work to be done there on how to kind of do a distributed encryption system. So that's kind of the fundamentals. Like I said, it's a fairly simple concept. If you just think of how tickets work in real life, then we're good to go on that. But the other interesting part about this, which surprisingly is, or unfortunately is a little more contentious, how do you actually carry this sort of information in packets? So the nature of this is we want to put data into packets with the express purpose that it's read by nodes in the network. That's not as easy as it sounds. So the way this is done today, and I'm not going to cover all of these. These are the various ways, the alternatives that people either have proposed or are doing. We know about stateful firewalls. That requires going into transport layer. But by the way, transport layer was never actually intended to be processed by nodes in the network, bit of an architectural ambiguity there. But stateful firewalls, they're in the network. This is kind of how they provide service, especially entrance into a network. Break end-to-end model, limited protocol support. Applications don't know about them. So my preference is, if stateful firewalls could go away from the internet, we'd all be better off. DPI, kind of the same problem. This is what happens today, even in the stateless environment. So service mappers will try to look into TCP or UDP, at least get the port numbers and try to reverse engineer what the application is. In the olden days, it was actually worse. They would actually go into HTTP and try to figure out if you're looking at a cat video or instructions to build a nuclear bomb. But those days are over thanks to TLS. So the good news is this one is a lot harder for providers to do. There's various other ways that are more proposals. Spud had an idea, put information inside the UDP payload that nodes in the network would actually parse into the UDP payload. That has problems. Segment routing is kind of interesting, but that really is only for limited domains. It wouldn't be useful on the internet. Flow label, kind of an interesting one. There is, people look at the flow label and they see 20 bits inside the IPv6 header, and they're like, oh boy, we could use those bits. They're not being used for anything. Well, they actually are. It's kind of critical to set them. Some people are using them for eCMP and RSS. So it's a little bit tricky. Also, the flow label and v6 addresses, which people have done, they have this other property that's really kind of tricky. Once they're set, they can't change for a flow. And clearly, one of the properties we want is to be able to set different services as the flow progresses. Distserv is kind of like the standard way you're supposed to do this, but there's so few bits, no authentication. Nobody really should trust distserv from the internet. Somebody says they want high priority coming from an anonymous source. Do you really want to give them that? There are solutions to this, but they involve rate limiting and kind of not exactly specific. So the proposal here, our old friend IPv6 hop-by-hop options. These obviously go back 30 years, I guess now. They're part of Internet Standard 80. They were actually designed exactly for this purpose. They work with any IP protocol. That's a benefit. So a UDP solution, for instance, can only work with UDP. They also have an interesting property. If there's hop-by-hop options in a packet, they must be at a fixed location in the header, which has a benefit over trying to find TCP or UDP header, which could be well into it. So we know where it is. It's still variable length. So that gives some of the vendors a little bit of a headache, but there's ways we can kind of make it seem like it's not variable length. It's also extensible. We can have as many bits as we want. So on paper, this is the right solution. I don't think anyone would question that. But it has an unfortunate history. And the primary problem is when we do the measurements on the internet, there's a 99% drop rate. If you send a packet with IPv6 hop-by-hop options, it'll probably be dropped if it leaves a local domain. So if you send out to the internet, that picture on the left, I could not find any country where it was not red. It looks like maybe a country in Africa might be a little off red, but they're dropped. And this is kind of sobering because a few years ago they did an analysis. It wasn't nearly this bad. It was like 50% drop rate, maybe 5 or 10 years ago. But the problem is the service providers, they basically did a BCP, best common practice, and pretty much said you should drop these. And the reason that they're dropped ends up being pretty obvious. A hop-by-hop option, by definition, is supposed to be processed by hops in the network. It's not directed to the destination. So the idea is these things are targeting my network infrastructure. So I'm not going to let these into my network because they're trying to affect processing on all of these intermediate nodes I have. Now, some of the background of hop-by-hop options that didn't help here. In 2460, the initial RFC on IPv6, they were actually required to be processed by every single node in the path. And what happened was some actually did process them. They throw into a software path. Some dropped them. But in the end of the day, they were kind of killed for that purpose. So I would point out, this isn't true of all extension headers. It turns out the destination options have a much better success rate because they are end-to-end. Also, I think Justin made a point that length matters. In the case of hop-by-hop options, even the slightest hop-by-hop option with the smallest length, it wouldn't matter. So that's the primary problem. The other problem, you probably would guess, is IPv6 only. That may or may not be a limitation. We can go back to the graph that Dave showed where we had the explosion of IPv6. So if you think in long-term solution, maybe this isn't such a critical problem. But we do have a slight mitigation for that. So this hop-by-hop options, it's something that we do have to deal with. Like I said, hop-by-hop options are the best solution. I don't see any other alternative that would scale to the internet like we're trying to do. So there are some mitigations that we're working on. The ones that I would point out right now, RFC 8200 says hop-by-hop options can be ignored completely by a router. So that's a big help. So no longer do they have to worry about putting those in the slow path. We do have a draft called Extension Header In-Flight Removal that I'll be presenting at IETF next week. The idea there is if your local domain supports something like tickets, then presumably they would support hop-by-hop options throughout the local domain. I mean, why provide the service if you don't provide the carrier? So you can be assured if your local domain ticket agent gives you a ticket, it should work in the local domain. So one of the ideas is, great, hop-by-hop options work in a local domain. Now the only problem is when I leave that domain and I keep the ticket attached, I don't want the packet to be dropped. So how do I deal with this? The kind of somewhat controversial way that I'm proposing is if a packet gets to your edge device, edge router, and it has one of these hop-by-hop options, which we know is probably going to be dropped, why don't we just remove that from the packet completely? So just take out the stuff that's going to be dropped from the packet. And we can take it out because it's really not needed by anyone else. We already said that, like in the case of a ticket, it's really processed by the first hop router, so it's not needed. The downside is obviously if it would have made it through to the peer by some miracle and it was reflected, well, we can't reflect it now because it's not there. So I think it's a small price to pay, and there's ways around that to extend it. So there's work to be done there on making extension headers and hop-by-hop options in particular use or work on the protocol level. But we also have some needed support in the Linux kernel that I wanted to mention. How do we make extension headers useful? And in this model, what we're really saying is the extension headers we're setting on a packet are bits that are coming from somebody else, and the application is really the one that's driving this. So it's the application that wants to set these extension headers. The problem right now with the kernel is extension headers are considered, I guess, risky because there's a lot of machinery, and it's kind of difficult to set a generic extension header without root privileges. So a while back, I did submit a patch that addresses a lot of this. It also actually helped a lot of things. It was a pretty significant patch. One of the things it did, it would allow applications to set certain extension headers, and it could be configured so we would have control over what they could send. So we don't want them to be able to send arbitrary information, but we could actually contain what they send to a meaningful subset. And then there were some other things, working with experimental IPv6 extension headers and what. Also, RFC 8883, that was approved last year. That's actually allows us to send ICMP messages when somebody drops extension headers. So there's work to be done. The patch, I guess, needed work. So I'll be getting back to that at some point. So to wrap it up, right now the status of this is it is a proposal that we are taking. I expect that this will be done in IETF because it is a protocol and because there's a lot of parties involved, right? So we need network providers involved, and it's not just an end host thing or a network thing. So IETF seems the right forum for this. We can actually up-level this one bit. A more broader topic is what we call host and network signaling. There's several instances of this, so we're trying to corral that. There's another kind of the opposite or maybe peer of this, which is network to host signaling, which is similar but has different properties. But I think both of these topics, they potentially could be percolated kind of like pretty up far up. I think we might have working groups coming out of these. They are common problems. There are a lot of different proposals for this. Obviously, if we can generalize solutions and come up with one way to do things, it's better. Like I said, we do need to move forward on the EH kernel patches, so there's some work to be done there. Going beyond that, the extension header limits I mentioned and extension header support in Linux, RFC 883. So those would be some good things to add. The extension header removal, very simple. Probably could do that in a simple eBPF, so that might be interesting to do. But then beyond that, kind of the normal thing, we'd be looking for recruits to potentially do a POC. That would involve all the way from the application to the network. My expectation is this would be interesting to some carriers. We've already had some interest from some of those companies. So hopefully we can get traction on that. All right, so that's it. Thank you.
Thanks. So first question was, when you mentioned tickets, my initial assumption would be that this is like an opaque token rather than a message that's encrypted and authenticated. That would allow fixed length, obviously, and multiple like AS on the network could all basically interpret the same token if it's generated by the client. Have you considered that?
So this was about why encrypt or?
No, yeah, it's about the format. Like a token is a ticket is usually just like an opaque something, right, that you carry. So I guess you didn't really go into the data format, but I had the idea that the data format is actually just a message, a carrier message that gets authenticated and encrypted. Could you just use a 64-bit, like a unforgeable or unguessable opaque token that the client generates?
Yeah, I was pretty vague on the requirement. Encryption is a strong word. I think sometimes we might call it obfuscation. So somehow, so I would look at it by the properties. So the first property is it needs some sort of authentication. We have validation, let's say that. So it needs validation, and we need to prevent forgery. So somebody reuses a ticket for their own traffic. So there needs to be some security mechanisms to bind to the ticket bearer, so, which I guess would be like the addresses. So we'd have to somehow bind to the addresses. And then the encryption part comes in, how much do you want to hide what is actually inside of that? And that's also a little bit of a question. So I did have an example here. I guess we don't have to bring it up. But the simplest format of a ticket would be to have a token, which is, I guess, minimally 64 bits you might be to get away with. So this token is quasi or pseudo randomly generated. Somehow the network knows what this token means. It has somehow it bears the information or a translation from the source address. So if you could get away with something as small as a token, that would be fantastic. There was also, interestingly enough, there's a separate proposal a while back. Giannis, I forget his last name. He did something called network tokens, which literally used the word token, but it was just it was a synonym for tickets for the most part. So we don't really have any hard requirements here. Well, the hard requirements are the properties, not the mechanism. So if we can find an efficient mechanism, if you have something up your sleeve that would just solve all these problems, that would be great. But bear in mind, this is one of those really hard problems because we're trying to do a distributed authentication on a public network with limited information. Fortunately, there are experts in this that can look at that. It's beyond my scope to really understand or to really do that. So I'm just going to stick with its properties. We need to do this, and security is important. You could make some arguments that if you constrain this to your local domain, you could actually even remove the tickets as they leave. That's fine, but if we do that, I guarantee you some people will stand up and raise the security flag. It happens every time. So it's just kind of one of these inborn things. Anytime we have a protocol, and this is one of the benefits of IETF, it has to go through some sort of security review. So my model is, okay, if somebody wants to run without any sort of security because they can confine this in a closed domain and they trust everyone, great. But we do need the solution, and you can't just kind of chuck the solution. So that answer the question, or?
Yeah, kind of. And sort of a question on a different topic, which is the Linux kernel code for the processing of hop-by-hop IPv6 headers. I think the IPv4 option code is like a mess. It's like very complicated, and parsers in the kernel are a potential vulnerability for crazy packets. So I guess my question is just how are we going to do this? Add more parser code for untrusted users in a way that is relatively easy to review for correctness. And
well, I mean, so in this case, the hop by hop options don't change, right? Because the content has to be validated. So it goes up to the application. They can deal with it, so to speak. The changes we need. It's a good point that you brought up IPv4 options, because a lot of people will say, can you use IPv4 options? The answer to that is pretty much no. They're even less usable. And also, there's kind of this general rule in IETF, we don't want to make improvements to IPv6 or IPv4.
Mm-hmm.
Kind of like what you said yesterday when you presented that slide saying IPv6 first, that was a 2 thumbs up, because that's a mentality we need, and that's been hard for the past 30 years. So IPv4, like I said, I'm less concerned about that. We do have a model where we could do it, but the kernel changes, they have more to do with just fundamentally making extension headers useful. There's nothing in particular about this use case that we need, other than the fact applications want to be able to set them.
Understood. I was just giving IPv4 options as a counterexample, because that code is hard to follow, and so it's easy potentially to for malicious packets to cause some kind of even a kernel panic. That code's there. I guess it's been fuzzed. With IPv6, if we add more code for extension headers, we just have to be careful about that aspect of parsing in the kernel is always a potential source of critical bugs, because it's bugs under the influence of external packets.
Yes, but
so it's just
that's kind of the kernel, right?
Yeah. Well, there are other things, but the parsers, the less we have to parse in the kernel, or the more we can parse in something like BPF, the easier it is to have some assurance that this will not blow up.
Yeah. So what I would envision is the only thing that's parsed in the kernel are the actual hop by hop options header.
Okay.
And pass the data to user space somehow. It does get a little interesting when you're doing that with TCP, but I think some of the solutions we saw were the last byte. If you attach ancillary information to the last byte when you do receive a message, that applies to everything. So there are solutions. But yeah,
so that already
point
exists.
Well taken.
Right. Okay, so that already exists, basically, a lot of this, right? The part that I would be concerned about, the hop by hop parsing. Awesome. Mm-hmm. Thanks.
What are the implications from doing this for net neutrality? Because, you're signing things. I think that problem in general is fairly solvable without the token part, unless you really want to bind to an application and make someone pay you money, right?
The application, the way I view it, it has a vested interest. Let me put it that way. So right now, all mechanisms to do this are essentially passive. There might be some application protocols. I think there might be some on 5G, but a general application asking the network something doesn't exist. And we've lived in that paradigm that, since the beginning of time. That's the separation of powers, right? But in this case, it's really the application that knows what it wants. So the way I would envision it is, yes, it's the application, but of course, we don't expect applications to rewrite themselves. A lot of this I would put in the libraries. It's kind of a mixed thing, but the security aspects of it, going back to some of Willem's points, it's really critical that we prevent applications from abusing the system. And that's, in a sense, that already exists. So that's why we have some lower layers that do these constructs. But in this case, the prevention comes from not filtering on a per packet basis, but more on what the application is allowed to send from the get-go. And that permission exists in some protocols. Trying to think, the network firewall protocol to establish it. So there's already things like this, but the difference here is when we get the ticket, the permission, there's no statefulness established in the network, which means we have to put it on a per packet. So the applications already do participate in these sort of things. I think we're just shifting the problem around a little bit, hopefully. All right.
We actually still have time.
Question.
We have 5 more minutes.
What would be the lifetime of a packet in the DOST environment? How can we avoid fast to becoming new TCP SYN flood? CDN protects the origin services by man-in-the-middle incoming connections, make fast efficient. Intermediates have access to the ticket. So that is true. The lifetime of the packet is a good point. The thing about the TCP SYN flood, though, and why it's so effective, is TCP SYN floods have there's no way to authenticate them. If we get a TCP SYN, there is absolutely no way to distinguish whether this is the attacker or not. In IETF terms, they say attackers never set the evil bit in packets. So the whole goal of a TCP SYN flood is to hide your attacking SYNs, mix them in with everybody else's, and then the denial of service attack is effective because the legitimate SYNs can't be distinguished. But in this case, for fast, the ticket itself ensures there's a certain amount of validation. So that's what we mean by we can't allow tickets to be forged. So it has to be some authentication back to the sender, which presumably would be the IP addresses. So if some IP address is sending a packet with a ticket, we validate that ticket is actually corresponds to that address. And if it does, then we process it. If not, it's a bad ticket and we just ignore it or take some other behavior, probably ignore it. There's no cost to ignoring fast. It's always best effort, unlike a SYN. So if we consider it best effort. Now, the obvious question there is, okay, how efficient can we make this validation process? That is, an open question, because now we have to potentially validate each of these fast tickets. But in some sense, I would also point out that's kind of similar to some of the things that we do in a TCP SYN cookie mitigation anyway, where we're installing some cryptographic cookies. So it might not be that bad. If we're doing a full decrypt and say decrypt's expensive, then you could argue maybe you have some sort of cache. So there's options here. But we have to realize it is a distributed problem, and there's a reason why TCP SYN floods and things like this are really difficult, because we're trying to do something in the middle of the network to validate host information. It's never an easy problem. And again, there are certain people who will point out how will this scale and how will this and this and this and this. So my belief is these problems are solvable. Obviously, we want to bring up every potential issue. But in this case, yeah, I think it's feasible. Also, we're compartmentalizing who really needs to process the ticket, so that's good. If we said that every single node in the network had to process a ticket, well, then that's a huge amount of cost. So we're kind of putting this at the edge. Also, probably could argue that this is going to be more efficient than doing a stateful firewall. So there's always pluses and minuses. But that being said, I guess this is also sort of a call to arms. So please, if you're involved in any of these discussions, if you go to IETF especially, please be involved in this, because one thing that's certain about a proposal like this, it is going to take a lot of resources. It's a fundamental change that crosses multiple boundaries. And like I said, we can't do any of this in isolation. So in order for something like this to succeed, it really has to be kind of a full stack approach, which is, in my opinion, that's the way a lot of things are going to go anyway. But in this case, so yeah, it's kind of a call to arms if you can help out on that.
So I don't know if Ivan raised his hand again. So the telcos love you, right? With this,
It's what?
the telcos must love this. I'm just trying to build up on what Jakub said about net neutrality.
Mhm.
If Verizon owns the phone, owns the agent that's running on my phone, what is that token even meaning when it goes across the network? Is it sending my message, my date of birth to Amazon, or this really happens actually
We'll
in the
be
past, right?
at the UE, right?
Well,
And then go as far.
the EFF sued sued Verizon for things like this, right? This is not even about giving you preferential treatment of the network, but rather privacy problems.
Yep. So it's all there. I mean, I guess a good starting point. So the current solutions, do they really have the attributes that we want anyway? I don't know. How do you even do a stateful firewall in Quick? I don't know if anybody ever solved that problem. So the protocols themselves have evolved such that a lot of these old techniques don't work. In fact, there was what do they call it? The IAB, Internet Architecture Board, kind of the steering board for IETF. They came out with a paper lamenting on the loss of transport layer information to the network. So, and Quick is actually the motivator for this. So one of the philosophies of Quick is they want to encrypt like everything, like all the transport layer. And of course, the network folks, they're all up in arms because they lost visibility. They first lost it with TLS, so they complained about that. Now they're losing it in this transport layer, so they can't do port filtering easily, and they can't do firewalls. Can't do application firewalls anyway. This whole company is built around this, so they're losing this ability. So they came out with this, and again, that's where they didn't provide an answer, but it was kind of like a call to arms. How do you solve this problem? Loss of visibility in the network. Which technically they never had, but it was abused for the past 30 years.
Yeah, of course, the telcos have been
There's
using it.
There's good stories behind this one.
Yeah. Okay, I think we'll wrap it up here. Thanks, Tom.
Okay, thanks.
Thank you.